Okay, well, I see we have our two folks, Abby and Pat, here, and it's great to have everybody. So, good afternoon, good evening, good morning, depending on where you may be. I am Dennis Lang, the CBO here at GelSight, and it's my pleasure to welcome you to this third installment of our webinar on webinars on roughness, telling the whole story with RNS parameters. Just as a brief kind of intro for those who may be new to the GelSight platform, GelSight's products precisely visualize and measure 3D topography of any surface anywhere, which will be demonstrated today on multiple materials, including metal, glass, carbon fiber, transparent and not transparent plastics, all of these kinds of things. Of course, a couple of the parameters that the industry sees most commonly today are the RA, the average profile roughness, and SA, average surface roughness or aerial roughness. But beyond that, there are many different surface roughness parameters that can be used to really get more intelligence about the surface your company's products deliver to an end user. So we'll get into how the GelSight platform, by digitizing that surface, allows you to apply the math to it to get these different parameters, and over time deliver and optimize products that you'll be putting out into the world. So during the webinar today, you'll see live demonstrations and applications of GelSight technology on these different surfaces and materials, an in-depth look and comparison at how several RNS parameters are calculated, the tangible benefits of our portable instant 3D analysis, which you'll see live. It largely speaks for itself, but it leads to time savings, better quality, safer processes. Finally, we will wrap up with a Q&A. So we will be going through the questions which are submitted over the course of the conversation here today. Please feel free to enter your questions in the Q&A seen at the bottom of the webinar panel here on Zoom. The other housekeeping reminder is, and you should have seen it when you joined, of course, but the webinar is being recorded, so keep that in mind as we participate in the webinar here today. Hopefully we keep it informal. It doesn't really matter. It's being recorded. It's for convenience. With that said, it's my pleasure to introduce to you Pat and Abby. So Pat Stack is the principal software engineer at GelSight. Pat has over 25 years of experience creating surface metrology, additive manufacturing, and CAE software of all kinds, and is a former member of the ASME B46 Standards Committee, classification and designation of surface qualities. So Pat very well understands the history and the latest state of the art when it comes to the math of doing surface analytics, and especially roughness, what we'll be talking about here today. Abby comes to us from an electrical engineering and software background and has been in the machine vision industry for nearly a decade. She leads the applications engineering team here at GelSight, helping customers create simple to use solutions for challenging measurement problems. With that, Abby will now show some live scans of roughness measurement on some machined aluminum to kind of get everybody aligned on what we'll be looking at here today.
Thanks, Dennis. So in the previous webinars that we've done so far, we've really highlighted the Series 2 system and measuring roughness with that. But today we also wanted to talk about the GelSight Max. So I've got both of them here. We've got two video screens going, but we've got our Series 2, which you've seen before, and we've got our Max system here. So the Max system is our highest resolution system that we have available, and really geared towards finer surface finishes down to that 0.2 micron RA range and up. The operating principles are the same between the two, but I'll go ahead and share my GelSight mobile software screen, and we'll go through taking scans and doing some analysis with both systems. So let me click share screen here. And we'll go over here. And I'll click go live. And I have the GelSight Max system connected right now. And when I press my fingertip into the top of this, you can get an idea of the resolution. You should see my fingerprint showing up on the screen here. Now I have this example of a sample part showed on both videos here, but we've got a highly reflective curved surface with some texture on there. And we'll go ahead and take a scan of this. So I'll just press the probe onto the top of this, and you'll see that machined surface texture. Now I mentioned the operating principles are the same between the Max and the Series 2. I'll actually take it out of live and take the cap off here, or take the gel out. You basically have a camera and a lens in here and 6 banks of LEDs. And when we capture a scan, we're taking 6 images with those, or taking multiple images with those different lighting orientations and getting 3D data from there. So that's the same between Series 2 and the Max. And once that 3D data is generated on the computer, we can open that scan up. So here we can see that surface that we just took a scan of, and we could go look at it in 3D. We've got an option for scaling here, so you can increase the scaling just to see some of that texture or curvature better. And then we also have an option to export this as an STL file from here if you wanted to do analysis somewhere else. And now we'll go back and I'll go in and I'll add a profile roughness function. For this, I'll just draw a line perpendicular to the lay of my surface texture, as we've talked about in some previous webinar sessions. And on the right-hand side, we can see the output. We've talked about configuring the filter cutoff, and we've talked about profile count before, but I'll go ahead and set up this analysis using multiple profiles. So maybe we want to look at 5 profiles evenly spaced within 1 millimeter. I can go ahead and set that up and click Analyze. And now I can see the average RA value as well, the average of all 5 of those profiles. And we can see our roughness profile on the bottom here. We also want to talk about surface roughness. So we talked about profile roughness, roughness along a line, and surface roughness will be our roughness over an area. So for that, I just selected surface roughness from my list. And I'll go ahead and I can configure a region or run it on the full field of view, but I'll go ahead and click Analyze here. I can also configure the form removal and the filter cutoffs from this as well. And one thing that we've mentioned before that's unique, that's pretty unique to the GelSight software, is the ability to mask a region. So maybe we see this little piece of something that was left on the machine part, and I want to ignore that from my measurement results. I can use one of our drawing tools down here, maybe just this circle, and draw a little spot to ignore, and I'll click Analyze here. And now we can see we can mask that region out. So this could help with measuring roughness around a feature or even around some debris or scratch or damaged area. And then we can turn this into our PDF report. So I just clicked PDF in the bottom left corner here. And here's the report that's generated to go with that. We can customize the views of the 3D data and the 2D images and what we want to include in that report as well. So actually, why don't we switch over to Pat? Maybe he can give us a technical description of what we just demonstrated with RA and SA in the software.
Yeah, if you've watched the previous webinars, we talked about RA in detail and how that roughness profile is computed and how the RA parameter is calculated from that profile. So I put this slide here together to very quickly show how the GelSight system will take an aerial measurement of an entire, in this case, it's probably, I'm guessing, 10 millimeters by 12 millimeters or so surface. And then you can actually define a line through that surface, and it extracts a profile from that line, which I try to demonstrate in that second image. And then the image at the bottom is actually the extracted profile. So what's really cool about GelSight is you get that 3D data very, very quickly, and then you can extract a profile anywhere from that 3D scan. Now, the SA parameter and the RA parameter are computed almost identically. The algorithm itself is almost identical, other than in the case of the roughness profile, you fit a line to the data and you adjust the tilt based on that line. For the SA parameter and all the S parameters, actually, a plane is fit through the data, and then the whole surface is adjusted according to that plane before the algorithm actually computes the parameter value. So this slide shows here that the S parameters are calculated from the entire surface that's been measured, and the R parameters are calculated from the roughness profile. Now, as I mentioned just now, the algorithm itself is almost identical, but the SA parameter is calculated over, in the case of GelSight Max, roughly 15 million data points. There's a lot of data. But modern computers can crunch that data very quickly and compute an average value. That average value is the absolute difference between each measured point and the plane that's been fit to the data. RA is very similar, but it's computed off of one line through that surface. And that line may have 10,000 data points as opposed to 15 million. So SA in general, I would say, is a more robust parameter because it's measured over so much more data. I get asked all the time, can I just substitute SA for RA? The short answer is no, because there's quite a bit of the difference in how, not the parameter is calculated the same, but how you come to that conclusion is a little different. The filtering, depends on the type of surface you're measuring, and RA value can change dramatically depending on how you define it on the surface. We're going to talk a little bit about that here in a bit. But the short answer is no, RA and SA are not compatible. Unfortunately, RA is the parameter that you would normally see on most mechanical drawings. And that's for legacy issues. For the last 30 or 40 years, that's what people have been specifying. Which is fine. It's good to check the surface texture of your parts. But if I was to be implementing, like if I had my own machine shop in my business and I was going to make parts for internal use, I would specify SA on the drawing because I think it's a more robust parameter because it's averaging over a large surface. But if you're making parts for another company or you're receiving parts from another company and you have to compare apples to apples from what they're measuring, you're more than likely going to have to stick with the RA parameter. Now, I'm not sure if Abby, you can go to the next slide here. Yeah, one of the things I mentioned, one of the reasons that RA and SA aren't totally compatible, you can't just substitute SA for RA, is for this reason here. A surface that's basically random, there's no lay or texture to the pattern to the surface, you could define that profile on the surface in pretty much any direction, and your RA value will be roughly the same. That's not always the case. A lot of materials, such as wood or something with a really defined pattern, if you draw your line parallel with the texture, you're going to get a much smaller value than if you draw it, perpendicular to the texture, which is typically what you would do. So for that reason alone, a lot of surfaces, the RA and the SA value won't correlate directly. Now, Dennis, like in the real world, like what are customers asking for? Are they looking for RA typically or SA, or is it a combination? I don't deal with customers as much as you do. What do you think about that?
Yeah, thanks, Pat. It's a good question. You alluded to it a little bit. Typically what we see from customers is a need to measure the RA value based on print. And of course, when an engineer or a industrial engineering team puts a print together, that print is based on the tools that are at hand and available at the time of the product. So GelSight, of course, in the aerospace industry and energy and other industries, sometimes is working on products that were designed quite a long time ago, long before our technology or technology like ours was available to very simply recreate the digital surface of any material. So when we do talk to customers, the majority in those legacy spaces for products that were not digitally born more recently, we do find they're looking for RA. But we do also find going forward, we are getting more and more questions about SA as customers and their design teams understand the value of bringing that data to their products. And of course, with roughness, as we've discussed before, there's a perception of product quality, there's real product quality, there's real product lifetime, and important decisions can be made on that. So in the end, GelSight, because we recreate that 3D surface and a user of a GelSight system has that data, of course, our platform really being hardware-enabled software, even scans taken years ago by GelSight user can have roughness applied to them today. So as that database grows, we do anticipate customers adding more of these values to bring more intelligence about their surfaces into their design process and their product lifecycle management. So it's a really unique opportunity that modern tools bring to the customer. And we look forward to working with more customers as we get more of those requests or there's new uh, math functions basically to be applied to existing data. And of course, for those watching today, at the end, we're actually going to share a call to action. We'll go through all of the parameters we calculate today. But of course, Pat can apply the math in a future build of GelSight Mobile to your existing scans to bring new parameters to that. So Abby, has Windows decided to let their USB driver work finally for your computer, or?
Well, since I'm sharing my screen, I would have to have closed the webinar to mess with it. So we're just going to go with the Macs this whole time instead of switching over to Series 2. But that's all right, because
Okay, great.
Pat said he liked it better anyways. So I can share my screen now and we'll do a couple scans talking about and highlighting this isotropic versus anisotropic surfaces. So let me jump over to the GelSight mobile software again. And we'll head back into Capture. And for this, I've got two different samples, which you should see me scan in the other video. We've got a 3D printed metal part, and we can see that those layered textures there. And then we also have some sandpaper to demonstrate that isotropic texture. So we'll go ahead and take a scan of that as well. And we can see all of the particles there in that surface. So now the scans are, the 3D data is generating right now and the data is being aligned. This is one other difference between the Macs and the Series 2 system. We actually have an advanced image alignment algorithm that is running on the scans to help compensate for any sort of effects from handshake, since we have a handheld system. And that's more important when we're looking at these higher resolution images. So we can we'll open up this scan first of that 3D printed metal block here. And I'll go ahead and add a profile roughness function. We'll just draw a line on our screen like we've been doing, perpendicular to that texture. And we can see the roughness output, the average RA and the other R parameters that we're calculating. We can see when we move the profile, there's a little bit of variation depending on where we put this profile. So this is a good example of when it would be a good idea to add more profiles to average the results. So maybe we want to do 21 profiles evenly spaced within 4 millimeters. So I'll go ahead and click Analyze. And now we can see when we move this around, the average RA is it's pretty consistent now that we're averaging all 21 of these profiles. But one thing that we'll notice, if we decided to draw the profile in this orientation, we're going to get a drastically different RA measurement or different roughness results and different roughness profile. So that's kind of to highlight the anisotropic features of this texture. So if we put this back in this orientation, we could also talk about surface roughness here, which should align decently well with that average RA value that we were getting there. Let's play in and look at this. So you can see these results are pretty close to each other, as Pat's saying, the math behind RA and SA is pretty similar, just over profile versus area. Now, if we wanted to jump over to the scan of the sandpaper that we just took, can take a look at it like this. I'll go ahead and add a profile roughness function here. And we'll draw a line just like all the other ones we've been doing. And let's go ahead and increase the profile count on this one too. Maybe we'll do 21 profiles. And we'll space them out again. We'll do 5 milliliters. And click Analyze. And we can see the average RA being reported there. It's close to 17. And maybe if we rotate this around, we'll put it back fully in the field of view. It's still pretty close, even when I'm rotating that line 90 degrees. So that will really show you the difference between this being an isotropic surface, and we can draw this line in any direction, versus when we were looking at that layered texture, where we can only really draw the line in one orientation and expect a certain range of values there. And we could even click PDF report here to kind of finish that workflow off too. So here's that PDF report for this analysis.
All right, thanks, Abby. Yeah, that sandpaper is one of my favorites because it's a subtle but very difficult measurement problem. Sandpaper media, of course, includes grains of various types of material that are sometimes clear, sometimes solid, and sometimes opaque. And of course, GelSight, given our technology, which creates a constant contrast with our gel, there is no challenge created by this for our system to measure. So on top of being a really nice example and a real world use case for us, where we talk to people about various abrasive, whether it's wheels or papers, but it shows really nicely that capability when you see it on the surface. As mentioned, when we think about the digitally born products out there, some of the more interesting use cases that we're starting to really find traction in are the additive manufacturing, as an example. Additive, being digitally born and creating things from scratch with better tool sets, is looking to increasingly use some of these parameters like SA and even others that Pat will be talking about here in a minute. They really allow the industry to bring next levels of quality using newer and future manufacturing processes, which historically might have actually even given metrology and inspection challenges, but today we are able to use in mass production. So when we think about some of those other RNS parameters, folks here today might not have the need based on existing systems to use extended palettes of RNS parameters. But we wanted to give Pat a chance to explain a couple of different parameters. RC and RSM are two we will be talking about today, that can share some definitions of those and really talk about how you might look to use these in your product mix going forward. So Pat?
Yeah, thanks, Dennis. That 3D printed part that Abby you just measured, it just reminded me how useful. I worked for a 3D printing company, and that GelSight tool would have been great for actually measuring the layer thickness. And the RSM parameter is perfect for that. If you were to draw a profile along the side of that part, you would have a series of peaks and valleys, obviously, representing the layer heights, the side of that part. And the RSM parameter, what it does algorithmically, it figures out what we call I refer to as segments. I think the ISO standard calls them motifs, but it's basically you're looking at the zero crossings of the profile, and you're dividing the profile into segments, basically peaks and valleys. One peak and one valley represent a segment or a motif. And the RSM parameter looks at all of those motifs that you find, and it finds the average value. So in the case of that 3D printed part, you could very quickly find out what your average layer thickness is. And that could be very beneficial for many reasons, but you want to make sure your machine is printing parts at the right layer thickness. If you're measuring a material, maybe like a pair of jeans, there's a nice defined pattern. You might want to find out that the machine is creating the fabric at the right spacing. There's all kinds of examples in the real world and a good use for RSM. And RC basically takes the work of the RSM parameter where it divides the profile into these motifs, but instead of reporting the average distance in XY, it reports the average amplitude or the Z value of the surface. So if you look at this chart, I try to demonstrate that. So it takes those motifs, finds the average peak to valley, and reports that. These are two more parameters that really come from the world of statistics. If you had a stat class in college or something, you might have heard of skewness and kurtosis. Those values are used outside of the world of metrology as well, but they come in useful for certain applications in metrology. And basically what the parameter does is it tries to quantify the overall shape or distribution of the heights in the profile. So if you look at that top chart there, you can see that the histogram computed from the profile basically has its peak below the mean plane or the mean line of the profile. So that tells you that there's more points below the mean plane of the surface. And in the chart below that has the skewness value. It's negative, but the distribution shows the peak is above the mean line or the mean plane of a surface. And these can be useful for a multitude of reasons. Quite often, when you have a surface that's going to be coming into contact with another surface, you may want to have an RS with a skewness value that's less than 0, which basically tells you you have more material above the mean height of the surface than below. And the typical example for that type of surface is a plateau hone surface, which is like a cylinder bore. You want to have a nice flat top to your surface. So there's not a whole, you don't want all these peaks sticking up that are going to get knocked off because of friction from the piston. But you also want to have deep valleys in your surface for oil retention. So RSK would be a really quick way to make sure the shape of your profile is close to what you expect. And then there's a whole nother family of parameters that can take that plateau hone surface and compute even more detail. And kurtosis is very similar to skewness. It comes from the world of statistics. It basically tells you for lack of a better term, the peakedness of your profile. If you could tell the skewness, the kurtosis value of that top profile is larger because it's got kind of spikes in it. And in the lower profile that they're more rounded off, the kurtosis value comes down. So your application, you're making a part, you may want something that has a skewness value that's negative and a kurtosis value that's low, below 3. Otherwise, you're going to run into problems due to friction. It's not going to wear properly. So these are just two simple parameters that can be computed very quickly and give you a general description of the shape of your surface.
Yeah, and I can jump over to the GelSight mobile software and we can highlight, we will go over an example of RSM. I've got this sample plate here with a bunch of fun textures and it's a transparent plastic material. So we'll go look at one of these and check out RSM. So all right, so we're back in the GelSight mobile software and I'll look at, let's see which one. This one I think will be a good one to illustrate RSM. So I just took a scan of that surface. And while that's generating and aligning our images, we can just look at a couple other ones of these. This is one of my favorite demo parts just because of the fun surface textures. All right, so we could also open up, after this one, I'll open up a scan, the same scan that I took earlier with the series 2 to show you the difference in the field of views and resolution between the two of them. But we've got this scan here. We could look at it in 3D again. And we can jump back over And let's do our profile roughness measurement. Also got our edges highlight overlay here. And I'll actually turn that off so that we can see some of the features better for now. But we'll draw our profile along this, perpendicular to this texture here, and we can see our roughness profile and the peaks and valleys showing up here. On the right-hand side here, we have the panel with our output, and we can see an RSM of about 673 there. So to kind of compare that to what we would expect, we can actually use our ruler tool. This is just a basic XY measurement tool in GelSight Mobile. We can just draw on the screen the distance between those peaks. So just eyeballing it, going in here, using the ruler tool, it gives me a pretty close value to the calculated RSM value from the profile roughness function. And because we're not doing the Series 2 live, I'll actually just go back over to another one of our scans from one we took earlier. I think it was this one here. And you can see what this surface looks like on the Series 2 system. So you can see a larger field of view, but a little bit less resolution there. And now I think you can see this long list of parameters that we output. So I'll actually jump back over to a slide to display all of those parameters that we have available in our software right now. So here's a list just to highlight both of those at the same time.
Yeah, I mean, I just mentioned that we're always adding parameters to this list, and you know, if somebody's watching this video right now saying that hey, the parameter that we use for our application isn't on here, please reach out to us and let us know. We could prioritize that, but yeah, there are literally hundreds of parameters out there between the ASME and ISO standards, and we're adding to this list, you know, every release pretty much.
Yeah, great. Thanks, Pat. So really appreciate everybody's joining the webinar here today and allowing us to demonstrate going through roughness with both GelSight tools and going through the software package to show what some of these different tools can do and why you might care about them for the particular surface you have. One of the interesting things we see, we talk about additive a lot for roughness here at GelSight because roughness companies have been some of our earliest adopters. And that bigger field of view with additive components tends to mean they buy the mobile instead of the GelSight Max. So the GelSight Max is the system extremely finely tuned for measuring roughness down to the 0.2 micron level, which we are doing today with several companies making very high resolution parts and many more of those to come, especially medical and other types of measurement challenges that we solve in a unique way. So thanks for allowing us to present these for you today. We'll give a minute or two for questions to come in. If there are any other questions out there from the team today, we'd love to hear about them. But pretty quiet out there, so if you want one, you'll get priority.
We must have covered everything.
That's right, Pat. Your explanation was so dialed that there's no need to ask or answer any questions about it. It's great. Okay, one question came in. I'll read it. This will be for you, Pat. So make sure you're ready. What is the difference between RSK, RSKU, and SSK?
Like I said, skewness is basically a quick way of determining if more of the material lies below or above the mean line of or in the case of a profile, it'd be the mean line. In the case of a surface, it'd be the mean plane. So the parameter, once again, just like SA and RA, the algorithm is almost identical, but one's computed off the surface, one's computed off the roughness profile. But the larger the skewness number, the more of the profile data that's below the mean line. Hopefully you can tell from that chart there. If you look, the gray area on the right is the histogram of the surface. So basically it's slicing the profile into little bins, and wherever the peak of that histogram is shows you where the most material is. I hope that makes sense. So when you have tiny little spikes like you have on that top profile, there's not a whole lot of material there. Most of the material lies below the mean line of that profile. So your peak of your histogram is below the mean line, and the skewness value is a positive number. So, and it's the opposite case. If you were to invert that profile, like in the lower chart, your histogram spike or peak would be above the mean line, and your skewness value is negative in that case. So it's a real quick way of getting a feel for whether your material is mostly above the line or below the line. And skewness is very similar. The actual equation to compute it uses power. I don't remember the top of my head, but it uses a power of 4 versus power of 3 for skewness. But it basically figures out, right in a standard, I think they use the word peakedness, which is, I didn't know that was a real word, but it basically gives you a good idea on how many, like you can see that first chart, it's got sharp peaks. So the kurtosis value is going to be larger in that case. And the bottom profile, the kurtosis is less than 3, so the peaks are more rounded. So it's, once again, there are many other parameters, but this is a quick way to determine the overall shape of the profile.
Awesome. Thanks, Pat. And again, as a reminder, the chat is turned off, the text chat, but the Q&A on questions is where you would submit those. Give it a couple more seconds here. Let anybody enter into the Q&A tool. But as we wait, I just say, if your questions, you don't want to have them answered here, or you think of them after the webinar, please feel free to send your questions to sales@gelsight.com. We'd be happy to get back to you there, even doing a live demo if necessary, or just respond by text. So with that, we don't seem to have more questions coming in. So with that said, unless any pop up here as we wrap up, we appreciate everybody that came here today and allowed us to present to you what GelSight is able to do today and tomorrow with the roughness tools, roughness measurement, the roughness mathematics, and even standards. And please, as always, reach out to us, sales@gelsight.com, info@gelsight.com, and we'll get back to you. So thanks, Pat and Abby, and thanks everybody for joining.
Thank you.
Thank you.
Bye.